To determine the maximum current per leg of a three-phase transformer, we use a specific formula. The formula is maximum current per leg equals total kVA divided by the square root of 3 times line voltage, with the result then divided by 1000. In this formula, total kVA represents the transformer's kilovolt ampere rating, which signifies its apparent power capacity. Line voltage is the voltage between any two phases in the three-phase system. The square root of 3, approximately 1.732, is a constant used in three-phase power calculations to account for the phase relationship between the three phases. The division by 1000 converts the result from volt amperes to kilovolt amperes, ensuring the final answer is in amps. To illustrate this, let's consider an example. Suppose we have a three-phase transformer with a total kVA of 150,000 and a line voltage of 480 volts. To find the maximum current per leg, we plug these values into the formula. Maximum current per leg equals 150,000 divided by 1.732 times 480, with the result then divided by 1000. First, calculate the product of 1.732 and 480, which equals 831.36. Then, divide the total kVA, which is 150,000, by 831.36. This yields approximately 180.43. Finally, divide 180.43 by 1000, resulting in 0.18043, which seems incorrect and means that we forgot to divide by 1000 earlier. Correcting that, we find that the maximum current per leg is approximately 199.5 amps. Therefore, the maximum current per leg of this three-phase transformer is 199.5 amps. Now let's consider another example with different values to further clarify the process. Assume we have a three-phase transformer with a total kVA of 75,000 and a line voltage of 208 volts. Using the same formula, maximum current per leg equals 75,000 divided by 1.732 times 208, with the result then divided by 1000. First, calculate the product of 1.732 and 208, which is approximately 360.256. Next, divide the total kVA, which is 75,000, by 360.256. This gives us approximately 208.19. Finally, we forgot to divide by 1000 earlier, so there is no correction needed and the maximum current per leg is approximately 208.19 amps. So, for this transformer, each leg can handle a maximum current of 208.19 amps. It's essential to remember the units when performing these calculations. The total kVA is measured in kilovolt amperes, the line voltage is measured in volts, and the resulting current is measured in amps. Furthermore, ensure that the kVA and voltage values used are the transformer's rated values, which can typically be found on the transformer's nameplate. In practical applications, the calculated maximum current per leg is crucial for selecting appropriate conductors, circuit breakers, and other protective devices to ensure the safe and reliable operation of the electrical system. Always consult relevant electrical codes and standards such as the National Electrical Code to ensure compliance with safety regulations. Now let's delve a bit deeper into the significance of the square root of 3 in this formula. In a balanced three-phase system, the three phases are equally spaced 120 electrical degrees apart. This phase difference results in a specific relationship between the line voltage, which is the voltage between any two phases, and the phase voltage, which is the voltage between one phase and the neutral point. A line voltage is equal to the square root of 3 times the phase voltage. Therefore, the square root of 3 factor accounts for this voltage relationship when calculating the current in each leg of the three-phase transformer. Another important consideration is the transformer's impedance. Impedance is the total opposition to current flow in an AC circuit, and it includes both resistance and reactance. The transformer's impedance limits the amount of current that can flow through its windings. The higher the impedance, the lower the current. Transformer impedance is typically expressed as a percentage of the transformer's kVA rating. For example, A transformer with a 5% impedance will have a higher impedance than a transformer with a 2% impedance, assuming they have the same kVA rating. The impedance of the transformer affects the fault current, which is the current that flows during a short circuit or other fault condition. A higher impedance limits the fault current, which can help protect the transformer and other equipment from damage. When selecting a transformer, it's essential to consider its impedance rating and ensure that it is appropriate for the application. It is also important to note that the formula we've discussed assumes a balanced load, meaning that the current is evenly distributed among the three phases. In reality, loads are often unbalanced, which can lead to unequal current distribution and potentially overload one or more of the transformer's legs. To mitigate the effects of unbalanced loads, it's important to carefully plan the electrical system and distribute the loads as evenly as possible among the three phases. Additionally, specialized transformers, such as zigzag transformers, can be used to reduce the impact of unbalanced loads. Moreover, the ambient temperature can influence the transformer's current carrying capacity. Transformers are designed to operate within a specific temperature range, and exceeding this range can lead to overheating and potentially damage the transformer. The ambient temperature, which is the temperature of the surrounding air, affects the transformer's operating temperature. Higher ambient temperatures reduce the transformer's ability to dissipate heat, which can limit its current carrying capacity. To account for the effects of ambient temperature, derating factors are often applied to the transformer's rated current. Derating factors are multipliers that reduce the transformer's rated current to ensure that it operates within its safe temperature range. These factors are typically provided by the transformer manufacturer and are based on the expected ambient temperature. Furthermore, the altitude at which the transformer is installed can also affect its current carrying capacity. At higher altitudes, the air is thinner, which reduces the transformer's ability to dissipate heat. As a result, transformers installed at higher altitudes may need to be derated to account for the reduced cooling capacity. The derating factors for altitude are also typically provided by the transformer manufacturer. Another crucial aspect to consider is the transformer's cooling method. Transformers generate heat during operation due to losses in the core and windings. This heat must be dissipated to prevent the transformer from overheating. There are several different cooling methods commonly used for transformers, including air natural, air forced, oil natural, and oil forced. Air natural cooling relies on the natural circulation of air to dissipate heat. Air forced cooling uses fans to force air over the transformer's surfaces, which increases the rate of heat dissipation. Oil natural cooling uses oil to cool the transformer. The oil circulates naturally through the transformer, transferring heat to the tank walls, where it is dissipated to the surrounding air. Oil-forced cooling uses pumps to circulate the oil, which increases the rate of heat dissipation. The cooling method used for a transformer affects its current carrying capacity. Transformers with more effective cooling methods can typically carry more current than transformers with less effective cooling methods. The transformer's nameplate will typically indicate the cooling method used. When selecting a transformer, it's important to consider the cooling method and ensure that it is appropriate for the application and the expected operating conditions. Also, harmonics can affect the current in a three-phase transformer. Harmonics are sinusoidal voltages or currents having frequencies that are integer multiples of the fundamental frequency. They can be caused by nonlinear loads such as electronic devices, variable frequency drives, and arc furnaces. Harmonics can increase the current in the transformer's windings, leading to overheating and potentially damage. To mitigate the effects of harmonics, harmonic filters can be used to reduce the harmonic content of the current. K-rated transformers are specifically designed to withstand the effects of harmonics. They have a higher capacity for handling harmonic currents without overheating. The K factor indicates the transformer's ability to handle harmonic load. A higher K factor indicates a greater ability to withstand harmonics. When selecting a transformer for an application with significant harmonic content, it's important to consider using a K-rated transformer or installing harmonic filters. In addition to the factors we've discussed, there are several other considerations that can affect the current in a three-phase transformer. These include the transformer's connection type, the type of load being served, and the overall design of the electrical system. The transformer's connection type, such as delta Y or Y delta, affects the voltage and current relationships between the primary and secondary windings. The type of load being served, such as lighting, motors, or electronic equipment, affects the current demand and the harmonic content of the current. The overall design of the electrical system, including the size and type of conductors, circuit breakers, and other protective devices, affects the voltage drop and the fault current. When designing an electrical system, it's important to carefully consider all of these factors to ensure that the transformer is properly sized and protected and that the system operates safely and reliably. Therefore, to accurately calculate the maximum current per leg of a three-phase transformer, you need to consider the total kVA, the line voltage, the ambient temperature, the altitude, the cooling method, the harmonic content of the current, and other relevant factors. Always consult with a qualified electrical engineer or electrician to ensure that the transformer is properly selected and installed and that the electrical system complies with all applicable codes and standards.